now. Okay. So can people see the screen?
Yes.
Okay. Okay. We're now in the second half of the course, integration. And so it is impressive how quickly we are moving. And what I want to do today is talk about one of the problems that motivated so much of calculus. And it goes back to physics. And this is the physics that you're doing in your class right now. We're discussing the motion of planets. And so, trying to understand the orbits of planets about the sun was the inspiration for the development of a huge amount of calculus. And so the big problem was trying to figure out, if we have something like Newton's law of gravity, and every mass is pulling on every other mass, how do we calculate the effect of something like the sun on a planet? Because the sun has so many small parts, each part is tugging. And Newton's great idea was, what if we could show that if we have a nice spherical object like the sun, that we might as well say that this is equivalent to all of the mass is concentrated at the center. And this is going to be true as long as you have a distribution that, the density is, symmetric and only depends on how far you are from the center. Then it's a beautiful calculation that you can assume all the mass is at the center. And we're going to use this to motivate the next half of the course, integration. So differentiation is talking about how things change. How quickly are we changing? What is our instantaneous speed? So if I give you a plot that tells you how far you've traveled at every moment in time, if you look at the slope of the tangent, that tells you your instantaneous speed. Integration is going in the other way. Instead of saying how fast we're changing, it's how far have we gone? So now, if my function, instead of giving you the distance from home, is giving you a speed, then the area under that curve is going to be the distance traveled. And so I'm going to try to motivate this idea of basically summing lots of different contributions by looking at what's going on for gravity. And so the idea is we're going to do another limit. So the fundamental limit in differentiation was the derivative. The limit is h goes to 0 of f of x plus h minus f of x over h. And this goes to 0 over 0, but goes in such a way that we actually get something that is meaningful. And we're going to do something similar for calculus. So we're going to try to find ways to sum lots and lots of contributions. So we're going to break the sphere up into more and more pieces. And in the limit, we're going to divide into infinitely many pieces. And for each piece, we're going to write down what the contribution is, and then we're going to try to find out what would be the contribution of everything. Now, we have to be extremely careful when we do stuff like this. It's very easy to have things that look reasonable, but are not. And this is why we have to prove things rigorously. This is why we have to be very careful when we're doing our arguments. There is a real danger in extrapolating and taking something that works in one region and saying it works everywhere. And we're going to see a great example of that in a moment. One of my favorite quotes is from Mark Twain: "A cat that jumps on a lit stove will never jump on a lit stove again, nor will it jump on a cold one." For each experience in life, draw only the lesson you should. Be very careful about extrapolating too much. All right, so let me just give you a quick rundown of how things are. So you've seen Newton's law of gravity. The force between two objects is proportional to the product of the masses and inversely proportional to the square of the distance between them. So if you go 3 times as far away, the force is going to be 1/9 as strong. If you double the mass, the force is going to be twice as strong. And this is an image from NASA. I think of an idealization of what it might be like for 3 planets traveling around a sun. Now, in most solar systems, especially those with just one sun, the sun is the most massive object in the solar system. But there can be other planets that have a significant pull as well. What do you think has a significant pull in our solar system in addition to the sun? Jupiter. And so you have to take into account the force of Jupiter. The planets that were classically known was Mercury, Venus, Earth, Mars, Jupiter, Saturn. And in the 1700s, they discovered, by telescope, Herschel discovered the planet Uranus. He originally proposed naming it after his king, King George of England. His king liked it, The rest of Europe said, hell no. And the compromise was to name it Uranus, who was Saturn's father. And for about 100 years, things worked very well. And then the orbit of Uranus was discovered to be a little bit off. And so there were two explanations that quickly emerged. One is that Newton's law of gravity was wrong, which was just terrifying because it had done such a great job for a century. And the other was maybe, just maybe, there's another planet. And if the planet is far out beyond the orbit of Uranus, it's not going to affect most of the planets. And it might only affect Uranus when they're near each other and they're traveling around the solar system near each other. And so they actually predicted where the planet might be. And two different groups, Adams in Britain and Leverrier in France, told astronomers where to point their telescopes to see the new planet. And unfortunately, Adams was not able to convince the people near him to point the telescopes, so he lost on the race to be the first to discover Neptune. And it was a monumental feat. It was described as basically the equivalent of being a rock star or a sports jock, in the 1800s. You predicted the existence of a new planet. It was absolutely amazing. And it fixed, for the most part, the orbits of all the planets, but not entirely. The orbit of Mercury was still a little bit off. So if you've just discovered Neptune and it's fixed the orbit of Uranus, what might you conjecture would fix the orbit of Mercury? Another planet. And where would you put that planet?
Closer?
Yeah, close to Mercury. And they put it very close to the sun, and they made it a very small mass so that it would have most of its effect on Mercury, but because it's so close to the sun, it wouldn't have too much of an effect anywhere else. And unfortunately, what is the problem about being very close to the sun?
You can't see anything.
Yeah, you really can't see anything. So the only chance you had to see it was during eclipses. And so they told the astronomers, on these days, you might have a chance of seeing it. And this was not in honor of Star Trek, but they named the planet Vulcan after the Roman god of the forge. And on certain days, they told people, this is your chance to see it. And most people, when they did the observations, could not see Vulcan. But a couple of people said, I see it, I see it. There's evidence for it. And this is a great example of the danger in doing science and having a bias in your measurements. People wanted to be the first one to observe the planet. This is going to lead you to international fame. So a lot of people, they're straining, they're trying to see, is that a planet? And it's very easy to be misled when you have a preconception of what you want to see. Over time, as the telescopes got better and better and better, they were able to make more rigorous statements about how big could planet Vulcan be, given that we're not seeing it well with our telescopes. And eventually, the size of Vulcan became so small, it wasn't going to be enough to fix Mercury's orbit. And it wasn't until Albert Einstein in general relativity around 1915 that they finally came up with an explanation of what was going on. And there's a couple of equations in physics you should know. So what's the equation involving F that you need to know in physics? F equals ma. The other one, which you might have heard, is E equals
MC squared.
E squared. So what
that's like nuclear fusion or something?
Yeah, it's basically saying that energy is equivalent to mass. And so it turns out that the gravitational field of the sun is actually equivalent to a little bit more mass. And when you factor that in, it fixes the orbit of Mercury. And it does fix the slight differences in the other planets. What was interesting is it wasn't discovered empirically until around 1919, 1920. And there was some controversy about Britain sending an expedition to one of the mountains to do the observation, because some people said, why should we British be proving a German theory of physics? And the scientists said, because this is right after what event? Right after World War I. And they're like, look, we don't really care that there was an international war. Physics is physics. There's not German physics and British physics and American physics. There's physics. Or you could do Sheldon. There's no such thing as a little bit of physics. There's just physics. And so, it was a wonderful, wonderful application of theory and experiment. So what I want to do is I want to consider the situation where imagine we have just a sun and a planet. And we want to calculate the gravitational force of the sun on a planet. And this is going to be the motivation for integration. So one of the things you need to learn how to do is what's called symmetry arguments, or without loss of generality. Without loss of generality, I might as well adjust my units so that the size of the sun is 1 unit big. Okay? I'm just choosing my units. And then I've put my planet, right on the y-axis. Well, I could have put it on the z-axis. I'm just rotating my axes so that it's in a very nice place. Is there anything wrong with that? No, this should actually be z-axis, not the y-axis, in terms of the code I'm using. I should have written z, not y, I apologize. Normally we put it in the z-axis right above the North Pole. Does it really matter? No. But why not choose a coordinate system that's going to make your calculations easy? So here's what we're going to do. I'm going to put in a bunch of points, and I'm going to approximate the sphere by putting in a bunch of points. So maybe what I'll do is I'll move over, 1/10 or 1/20 or 1/40, and look at all points x, y, z, where x, y, and z are going to be between, well, minus 40 and 40, but I need to be a unit sphere. So let me adjust. So maybe it's going to be x over 40, y over 40, z over 40. And so I'm going to have a really fine mesh, a really fine cubic lattice, a 3-dimensional lattice. And each point is going to be, my approximation to the sun. And I only care about the points such that the x coordinate squared plus the y coordinate squared plus the z coordinate squared is less than or equal to 1. That's the equation of a sphere. Do you agree that the finer mesh I take, the better approximation this is going to be to a sphere? If instead of doing x over 40, if I did x over 400 or x over 4,000 or x over 40,000. And the hope is that in the limit, as I take a finer and finer mesh, this is going to converge to what the sun is actually, this 3-dimensional object. And for each point, I can calculate what is the force on my mass, that's on, say, the z-axis at some height. If there's only finitely many points, do you guys know how to do the calculation? Yeah, we just use Newton's law of gravity. And as long as there's only finitely many points, so what we're going to do is for every point that's inside the sphere, we're going to calculate what the force is. And then we add them all up. And that's what integration is all about, is for every point in your region, you assign a value, and then you just add up all the contributions. And so on the left is some code that I wrote to do the calculation. And the right is some comments. And the really only comment I want to talk about is the ability to write code that runs well. This code took, I think, a decent amount of time to run. So x and y go from 0 to the range, and I'm going to take the range to be 40, but z goes from minus range to range. And the reason is we have some symmetry. So if we have a point just above the North Pole, above the sun, what's going to be the direction of the force on it? Towards which part of the sun? Towards the center. So it's going to be pulled straight down. So the point x, y, z and negative x, y, z and x negative y, z and negative x, y, z, they all contribute the same amount. So I can actually save time by not looking at all the possibilities, but just looking at a point x, y, and z, and then negative x, y, z, negative x, negative y, z, and x negative y, z all give the same contribution. I just have to be a little bit careful, because if x is 0, then they're not all going to be distinct points. And if y is 0, they're not all going to be distinct points. This is just saying, by being a little bit clever, I can actually increase my program to run 4 times as fast. And on the next slide, you'll see the results. So the slide on the left, can you see the 2 different sets of dots? On the left, in the left plot, do you see 2 sets of dots? So for each x value, there's 2 dots. Can you see the 2 dots? Does anybody see the 2 dots?
Yeah, yeah, I do. I mean, there's like the dot there and there's the dot in the one to the right.
Right, but I'm saying, do you see 2 different colored dots on the left?
No, I
No.
see.
And the
Wait,
reason is I'm plotting the force if you assume all the mass is at the center. And I'm plotting the force from approximating the sphere with this grid of dots. Okay. When things are this close, rather than plotting their values, it's much better to plot their differences. So if you look at the second plot, this is plotting the differences. So can somebody tell me roughly how much is the difference?
0?
Be more specific. You can do a little bit better than 0. Look at this. About how big is the difference?
-6 times 10 to the -6.
Yeah, so it's about 10 to the -6. So 10 to the 6th is 1,000,000. So this is basically telling you it's about 1/6 million. Okay. This is a small difference. Okay. So do you believe that as we take a more refined mesh, smaller and smaller, it's going to converge to the same?
Yeah.
So in your physics class, have they talked to you about you can say that all the mass is at the center?
Yeah.
So this was the big integral that Newton had to do. He had to show that you could assume that all the mass is at the center. Because if you can do that, now all of a sudden you just have 2 point masses acting under gravity, the center of the planet and the center of the sun. And even if you put in the other planets, it's not so bad. But you remember his law is every object in the universe attracts every other object in the universe. And if you have the sun and you have to calculate every single time the effect of each point, the calculation is just terrible. It's terrible today with our supercomputers. Imagine what it's like in Newton's time, when they didn't have the supercomputers. So do you think an error of size 10 to the -6 is going to go to 0 as we take a finer and finer mesh? Seems reasonable, but we have to be careful. And so what I want to end is a quick comment about Albert Einstein. So he won the Nobel Prize. He had 6 groundbreaking papers in 1905. 3 of them, I think, individually would have been, each one of them, I think, would have been enough for a Nobel Prize. He had an incredible year. And one of the consequences of his theory of special relativity is that your notion of speed is wrong. So if you're on a train traveling at 100 miles an hour, and you run on the train in the same direction of the train as at 10 miles an hour, how fast does somebody on the ground see you going at?
Well, less than 200 miles.
Well, no, the train is going at 100 and you're running in the same direction of the train as 10 miles an hour.
110.
So people would say it looks like 110. And when they did the experiments, it looked like 110. But what Einstein proved is it's a little bit smaller. So if the train is going at V and you're going at U prime, the person on the ground sees you traveling at U, which is V plus U prime. So it's the sum of the speeds divided by 1 plus the product of the speeds divided by the square root, divided by the square of the speed of light. So the speed of light is 186,000 miles a second. It's incredibly fast. To put things in perspective, the Apollo 11, when it went to the moon, I think its maximum speed was around 25,000 miles per hour. Light is traveling 186,000 miles a second and is 3,600 seconds in an hour. So if V and U prime are very small relative to the speed of light, this correction factor is going to be so close to 1, it's going to be very hard to see. And this is the real danger that I want you to be aware of. Just because something looks reasonable does not mean it is. When people were trying to deduce the laws of physics, one of the things they said is it looks like the sum of two speeds is just add them. This is reasonable. It's a good approximation when the speeds are small, but as the speeds start to get close to the speed of light, it is not that reasonable. Why do you think people didn't notice this in Newton's time?
There's something wrong with it.
Well,
They didn't notice it.
so first of all, people didn't even know the speed of light was finite. The second one was that there was nothing man-made that was going anywhere near the speed of light. And in fact, the first time they discovered the speed of light was finite, I believe, was looking at the orbits of Jupiter's moons. And it had to do with, when the moons were on the close side or the far side of Jupiter, their motion seemed to be a little bit different. And it was because of the finite time it took light to travel, that in one case it had to travel a little bit further. And that's why some of the measurements were a little bit different. So what I want to end with today is a plot of the difference between the classical speed, where you would just add the two, and the relativistic Einsteinian notion, where you would divide by this factor. So I'm plotting the difference. So when you look at the plot on the left, let me zoom in on the plot on the left. How big of a difference do you see? About how big is the difference?
10 to the negative 6.
10 to the negative 6. This is about the same order of magnitude as what we just did with this approximation for replacing the sphere with a bunch of points. It's the same order of magnitude. What I'm doing here is I'm shooting, I'm on a rocket ship or a really fast train traveling at 10,000 miles an hour. And then my x-axis, the value there is how fast the bullet is that I'm shooting. So if the bullet's going up to 10,000 miles per hour, we're seeing almost no difference. On the plot on the left, I'm getting closer and closer to the speed of light. The speed of light is about 6.7 times 10 to the 8 miles per hour. Over here, when my speed is about 6 times 10 to the 8 miles per hour, the change is only about 8,000 miles per hour. The change is still extremely small when we're close to the speed of light. And so it takes a long time for us to get to a place where we're really going to see a difference. So this is the motivation for what we're going to be doing in calculus. It's how do we deal with sums? If we have finitely many terms, we can just add them. But what we want to do is we want to take complicated objects and break them down into smaller and smaller pieces and find the contribution for each. So the way you should view this is at every point in the sun, we attach a number. And that number is going to be the net force it has on the planet. And then we want to just add those numbers over the entire sun. And that total sum is going to be the net force that our planet feels. And this is the second half of the course. It's going to be figuring out how to do stuff like that. All right, so I think this is a good place to stop. I will wish everybody